Hello everyone, my name's Kerr from New Energy Update, and thanks all for joining our webinar with EDF and 3M today. I hope you can all hear me. If you have any problems during the webinar, you can always send in questions through the chat tool. You can send them directly to me, or you can use the chat function throughout the webinar. And yeah, that's basically it, and we're all ready to go. So welcome everyone to New Energy Update's free blade maintenance and optimization webinar in partnership with EDF Renewable Services and 3M. So why are we here? For years, wind farm owners have neglected the condition of their blades, only to realize now that a good strategy for inspections, repair, and condition monitoring will boost production and slash failure costs. As today's webinar will show, EDF has found that a combination of good maintenance and excellent innovation has helped them to increase turbine AEP by as much as 23% a year. Now they want to share their learnings with you. We will be joined in this webinar by Charles Casmer, current account manager at EDF Renewable Services, Brett Anderson, key account manager for 3M, and Jerome Lahire, generation manager at EDF Renewable Energy. They will help you learn how to take advantage of the latest blade maintenance best practices to gain even higher AEP and portfolio revenues from extended blade lives in all of your assets. They'll also explore the proven benefits of vortex generators as an invaluable tool that will help you achieve return on investment in under 2 years. You'll be able to send in your questions at any time during our webinar. So if you have any technical problems, just drop me, the organizer, a message directly through the chat function. Finally, before you all ask, you will be sent a copy of the recordings of this webinar tomorrow. So that will be sent automatically via GoToWebinar to you around this time tomorrow once the recordings are processed. So thank you very much to everyone in advance. So now it's over to Janae, who's going to walk us through the rest of the webinar.
Hi, this is Charles Casmer. Here, thanks for handing it off. I'll go ahead and start off this webinar. Everyone, thank you for joining us today. EDFRS is a company with 30 years of experience in the wind industry. We currently have 10 gigawatts of assets under contract. At EDF, safety is the foundation of our business, and our safety record reflects this with a low TRIR and a low DART score. I would like to thank Brett and Jerome for joining me today to discuss blade management and optimization. Both of these topics can have a huge impact on the AEP of your assets. AEP being the amount of electricity a generator produces over a year. A generator's output may vary based on equipment condition and performance. Let's talk about how we enhance AEP. There are multiple options to enhance the AEP of your asset. 2 ways are pitch optimization, which is tuning of the pitch parameters during the different seasons of the year, along with yaw optimization, which is the yaw alignment correction. We also have blade inspection and repair, blade aerodynamic optimizations, which are add-ons to the blade, along with major component hardware upgrades, which can be drivetrain upgrades, blade extensions, along with repowering efforts. During this webinar, we are going to focus on blade inspections and repair, which is key to a good blade maintenance program, along with blade aerodynamic optimization. Maintaining your blades during the first 10 years are key. A realistic pro forma should be created to allow the project to properly maintain and protect the asset to maximize production of PTC credits. So the vision. We all wish that our blades would stay in the same condition as they were at the date of installation. Sadly, we all know this is not true. The blades are the most exposed piece of equipment on a wind turbine. They are exposed to all kinds of weather elements like wind gusts, rain, hail, ice, and lightning. The reality. Without proper maintenance of your blades, you risk catastrophic failures. These failures carry high dollar values, not only for the replacement of the failed blade, but due to the risk of consequential damage to the tower, the nacelle, and other blades. These replacements also represent unique safety challenges for the teams that are replacing them. Let's talk about the common blade failures. Number one blade failure in the industry is going to be lightning strikes. The risk of lightning strikes has increased with the use of carbon in the design of new blades. Another damage that we look at is leading edge erosion, which is the erosion of the blade leading edge due to contamination or precipitation impact. Then we have laminate delamination, where the layers of laminate have become separated from themselves. These two failure modes can cause moisture ingestion, which allows water to seep into the laminate. This is a compounded problem when we have freezing and thawing cycles, when the moisture freezes and thaws within the laminate and allows the damage to grow and worsen. And lastly, manufacturer defects. This has become apparent lately due to the increasing size of blades and the rapid response to deploy larger rotors. Damages from the factory include uncured laminate, lack of glue, shear web and spar cap cracks, detached LPS cables, wrinkles in the alignment of the fiberglass, and dry fiberglass. So the key to a proper blade maintenance program is having a damage classification program. Within EDF, we have 5 different categories. We have cosmetic damage, which is the basic damage, which would be contamination on the blade surface discussed on the gel coat. For these type of damages, no action is required. This is just normal wear and tear. The next level is our grade A, which is our true minor damage. These are damages that we recommend repair within 12 to 24 months, monitoring during that time for the propagation. And with minor damages, we're looking at small areas of damage on the top coat and gel coat, along with small areas of erosion. Our next category will be our grade B, medium damage. This is damage that we recommend repairing within 6 to 12 months, and during that time, monitoring the damage for progression. These would be small cracks or areas of delaminate exposed, along with small lightning strikes. Our next classification would be our grade C, which are our major damages. These damages we would recommend to repair within 6 months with continual monitoring within that time. This would be large transverse or longitudinal cracks, along with large lightning strikes and areas of delamination. And lastly, our grade D, which is critical damage. This is damage that we would recommend the immediate stop of the turbine due to the risk of catastrophic failure. This would be leading edge and trailing edge splits, or damage in the structural areas like at max chord. Not all damage is equal. 2 areas of damage of the same size can be different damage categories due to the loading in that area. This is why it's key to have a detailed grading procedure so that the process is repeatable. So let's talk about the different methods of inspection. The basic inspection method that has been used since the start of the wind industry has been visual inspections. These are typically included within the planned maintenance of your wind turbine with your O&M contract. It is a visual inspection typically using binoculars or a spotting scope and performed by the technicians before they go up tower. The technicians note any damage, and any damage that is noted should be followed up with a photographic inspection for monitoring repair recommendations from a blade specialist. The next option is photographic inspections, which, as I stated, should be used to follow up any defects identified with visual inspections. You can perform manual photographic inspections of your park, but this is a very time-consuming process. I would recommend that you utilize an automated system that needs minimal input from a technician when looking at park-wide inspections. The next option that was used for years was rope access inspections. Technicians secure the blades using ropes to send the blade to inspect every area of the blade. They are visually able to inspect the blade and note the size of damage and perform minor repairs. During the inspection, they can also mark damage to monitor the progression of the damage. They can determine if cracks are isolated to the gel coat or have progressed to the laminate via non-destructive testing. In the recent years, UAVs and drones have become the new park-wide inspection method. Drones can be controlled by a certified operator or automated to perform the inspections. These inspections, when automated, can be completed in less than an hour. The drones take detailed photos or video of each blade with minimal direction from a certified operator. A new inspection method that has come to light in the past 2 years is thermal imaging. Thermal imaging allows you to see the different temperatures along a blade in respect to defects via the changes in the airfoil. In the picture, you can note that there is leading edge erosion in areas, along with a strip of VGs that is missing. You can also use thermal imaging to detect subsurface cracks. I'd like to note that for any identified defects, you do have to follow up with a hands-on inspection to perform non-destructive testing to determine how deep the damage is. External inspections are the normal inspections we talk about when we're talking about blade inspections. But you should also look to internal inspections as a key piece of your blade maintenance program. They can be used to identify structural defects on the shear web and spar cap along with the trailing edge. There are 3 different methods to perform internal inspections. Technicians entering the blade via confined space is one. This gives you hands-on inspections within the blade, but is limited to as far out as the technicians can go as the blade goes towards the trailing edge. Another option is utilizing robots. Robots are able to reach the tip of the blade where the technicians cannot fit. You also get detailed photographs as the robot descends the blade. We also have camera inspections, where a camera is lowered at the 6 o'clock position via rope to take both pictures on the leading edge side of the shear web and the trailing edge side of the shear web. Inspection considerations. You always want to plan to perform your inspections following the high wind season. This allows you to catch damage that was accumulated during the high loading season and allows you to schedule repairs in the low wind season. A key inspection in the life of the wind farm is your end of warranty inspections. This is where you get your biggest bang for your buck with respect to blade inspections. Finding a single failed blade or a few category C or D defects can pay for the whole park-wide inspection. It also gives you the baseline for your post-warranty blade management program. Into warranty is a good time to perform internal blade inspections. If your budget only allows you to perform a small population of inspections, focus on turbines with high turbulence, wind gusts, or emergency stops, where you're seeing the highest loading. Lastly, you need to have a data management program in effect. Inspections generate a ton of meaningful data. If you're performing inspections in-house, you need to set up a database to manage the photos and inspection reports. When selecting a provider, you want to pick a provider that customer portal meets your needs from a data retention and interface perspective. Let's talk about repairs. There are multiple methods to perform repairs to your blades. We have rope access, which is, again, technicians descending the blade to perform category B and C repairs. We have platform work, where you have a 360 platform or a man basket. Technicians are able to address all variety of blade repairs utilizing this platform. We also have a boom truck or a man lift, where technicians are quickly able to install add-ons as they don't have to reposition ropes or a platform. And then we have ground repairs, when the damage is so severe to your blades that you have to lower the blade to the ground to perform structural repairs. Let's talk about some other repair considerations. One being blade cleaning. Through the life of the operation of the turbine accumulates contamination buildup on the leading edge along with oil and grease. This can impact your AEP, and you should put in effect a blade cleaning strategy using a vendor that uses biodegradable cleaning solvents. This can be performed via rope access or a boom truck. Also, when you're performing lightning repairs, ensure that your provider is performing LEP testing once the repair is complete. You need to ensure that your lightning protection system is functional so that you don't incur damage later on with additional lightning strikes. And selecting the right provider. Due to blade repairs being high-risk work, always review the company's safety record and policy. Due to the high demand of companies during the low wind summer months, it's best to qualify multiple providers. You should also look at providers that complement each other. Look to pair providers that can only provide non-structural repairs with a company that has engineering resources for those structural repairs. Let's talk about lightning damage repair progression. As you can see, we have a blade that has suffered a lightning strike. The first step is to remove the gel coat and perform non-destructive testing via a tap test to determine the areas of laminate that need repair. Once that you identified those laminates that need to be those areas of laminate that need to be repaired, you should grind away the damaged laminate. Then you will repair the foam core, put your layers of laminate on, and allow it to cure. The last step is going to be applying gel coat and reapplying leading edge protection to protect your asset. This was a very simple walkthrough of a lightning repair. As most of you know, these repairs can be quite in-depth. Lightning strike repairs average 5 days, with severe damage requiring a tip mold taking up to 14 days. The price tag for these lightning repairs can range from $20,000 to $50,000 depending on the severity. And if you have a lightning strike that has damaged a carbon spar, usually that results in a blade being dropped to the ground for repairs. The progression of leading edge erosion. As you can see in the first picture, we have a small area of leading edge erosion. As the years progress, the damage on the leading edge progresses as well, which can lead to a expensive fix in the long term, as you have to prep that area for repair and LEP reapplication. Along with the cost of repairing the damage, the performance of your asset can also be impacted with the reduction of AEP. When we're talking about blades, the repair cost for blades increases nonlinear as we work our way through the gel coat and into the laminate. Damage can cause a significant loss in AEP. When we look at pits and gouges, we can see reductions from 3 to 8%. Delamination and severe erosion, like we see on the picture, can cause up to 20% reduction in AEP. This is why it is critical to install LEP early on in the project, as the repair of the surface of the blade for application of LEP can take up to a day when we see severe erosion. I would like to now hand it off to Brett.
Thank you very much, Charles. So we began the discussion talking about inspection and repair, and now we're going to move along and talk about protecting and upgrading. And what we'll do is take the next 15 minutes or so and talk a lot about aerodynamic efficiency, stall, and how it can negatively impact AEP. We'll take a look at 2 common contributors to stall, and then 3 specific aerodynamic optimization opportunities that everybody can consider. And then we'll look at a couple of solutions that have been demonstrated to improve AEP. Okay. Before we move on, I just pause for a moment and kind of reinforce some of what Charles was talking about. So on the slide right now, the chart in the lower left basically is showing 2 different kinds of damage. So the dark blue are minor and frequent. So these are the kinds of activities that your asset teams on the ground are kind of dealing with on a regular basis. And then in the lower 4, light blue, are major and less frequent. And go ahead. The highlighting in particular blades, if you look at the average downtime per failure, you see that blades, by and large, have the longest average downtime. And so preventative maintenance, paying attention to leading edge and performance, can dramatically impact AEP from an operational and also from an availability perspective. Next. So what I like to do to kind of set up the rest of the discussion is just talk about stall, and we're going to talk about 2 different kinds. So one is stall on the upper skin of the blade, nearer the root, it's aerodynamic, and then stalls created by leading edge erosion, typically outer third, outer half of a blade. And we'll go to the next slide. And you can see that some dramatic photo on the left of some very severe leading edge erosion that contributes to stall. And on the right is the image of the turbulence or the stall on the upper surface. And go ahead. What we'll be talking about is leading edge protection, primarily some tapes for resolving or trying to mitigate some of the damage for leading edge protection, and then vortex generators, because these 2 behaviors are basically robbing you of AEP the way, just kind of in small pieces. And so we'll go to the next slide. The next three slides, we're going to take a look closer at specific aerodynamic optimization opportunities. This first one is really a function of blade design and how the blades work. And so there's two things that are having impact. So there's blade twist and then the limited chord length. The key thing to take away is if we look at the charts on the right, both top and bottom, this gap that we're looking at is the black line is your conventional blade, and then the red line is optimized. And so if there's a way to bring those lines closer together, to bring optimized closer to real, there's AEP to be gained there. And so we'll talk about closing that gap and extracting more AEP from this particular optimization opportunity. Okay. And then the next one is the stall on the upper surface of the blade. And what this is really interesting, for me anyways, because if you look at the charts on the right, this example shows the more aggressive your angle of attack, that you can increase lift, which is a good thing. It's what we all want. But if you look at the chart on the bottom, as you increase lift with the more aggressive angle of attack, you also increase drag, which is bleeding AEP from the production. This slide we're talking about now is the leading edge erosion that leads to significant energy loss with stalls. And so Charles mentioned this earlier, that this can have this effect, and this really is why. So if you just go ahead with the arrows, please. There's a difference between the coefficient of lift on a clean or pristine leading edge and an eroded one. And there's also a difference on the coefficient of drag on a clean or pristine leading edge as opposed to an eroded one. And so whatever we can do to preserve the integrity of the leading edge longer contributes positively to AEP for the machines. So if we look at the next slide, please. There's really, the questions are reducing the impact for stall with leading edge erosion by installing the appropriate leading edge protection, and then reducing stall from aerodynamic inefficiencies by vortex generators begs the question, how much AEP is available if we look at these three examples of optimization? And so if we look at the next slide, we're talking about leading edge protection. This was an interesting study where it's a comparison of the blade's AEP performance originally as dirty or rough, i.e. eroded, and then once there was a maintenance program on those blades, looking to see what kind of improvement there would be. And we can see here that the total power return increased 3 to 8% per year. So it's closing this gap on the leading edge by maintaining the leading edge is one way to effectively increase or impact AEP. Okay. And just wanting to highlight a couple things here. Go ahead, please. That you'll note that leading edge protection, highly durable, in place on more than 150,000 turbines since 1994, significant reduction in leading edge erosion, and then extended maintenance and service intervals. Much of the discussion that we're having right now is around AEP and trying to extract that margin of 2, 3, 4, 8% more energy from the turn of the blade. But just a comment around the benefit from a maintenance practices, our first generation of leading edge protection tapes would withstand about 9 hours of testing at an independent lab. And we know that that particular solution would end up in service lasting about 5 years in the field. The newest generation of leading edge protection that we're offering now, with that exact same testing, is lasting 50 hours. So if 9 hours equals 5 years, 50 hours in that testing, we're thinking, 15, 20 years, basically life of the blade kind of solution when properly installed. So if we go from talking about leading edge protection, next we'll talk about vortex generators. And this slide is very straightforward, and it kind of highlights some of the comments I made earlier, where you see In low wind speed, we see about a 3% increase in AEP. High wind speed is about 1.5. And this really is kind of proof of that discussion we had about a more aggressive angle of attack, increases lift, but how do you counteract the coefficient of drag or the stall? And that's really where the VGs can be very powerful. So we see about a 3% increase and payback in 1 to 2 years, okay? As a summary, we're just talking about more than 1,000 turbines from various OEMs that have been successfully equipped. We see generally 2 to 3% is the increase, and I've got a slide here in a little bit to show more about how we kind of arrive at that. And we look at that payback period around 1 to 2 years. So let's just take a closer look at vortex generators. They're not new, but it's good to get everybody grounded on kind of how they work and how combination of EDF as an installer and maintenance provider, 3M with our technology, and the partnership that we have with SmartBlade makes it such a powerful tool. So VGs are aerodynamic devices to basically delay flow and to reduce stall effects, okay? The next slide. So this, what's interesting is, so you have a aerodynamic device, you get it installed, and basically knowing exactly where to put it to maximize the benefit is really where the resources of SmartBlade and this SmartViz visualization system is very powerful. Basically, we're talking about flow visualization, okay? And how we get there is multiple tools, so ground optics, blade sensors, wind measurements, some very heavy-duty number crunching. This is truly big data to do the modeling and to pull the measurements exactly from the blades as they operate and compare them to a turbine standing right next to them, so you get a true measure of impact in how the VGs work, okay? That's really demonstrated here. When you look at the image of this blade, you see that these tufts have been placed along the surface of the blade. You note that they are randomly organized, some point left, some point right, and then on the image on the right, you see that once the vortex generators have been installed, all of these tufts are organized very neatly. Basically reattach the wind back to the blade surface to maximize AEP and the energy generation. And this next slide just shows you kind of a cartoon of that, but just kind of represent what's going on, and that the application of vortex generators helps us prevent that stall, brings the air back onto the surface for maximum energy, and gets rid of that large drag, that large stall condition that's happening, as shown on the cartoon on the right. Next slide, please. So we see that the vortex generators can definitely have an impact on AP. I've been in this role for about a year, and one of the questions I get asked is, how well do they stay on? How long will they be on the blade? And we know that the VGs are in a very challenging environment, wide temperature variability, multiple flex forces, and differentials between the VG and the blade itself. And we know that liquid adhesives, typically when they cure, lose their ability to flex and become very rigid. And so then when you have difference in flexibility, difference in density, things like that, you can have a tendency for some of those to pop off. And so what we use on these VGs is one of 3M's acrylic foam tapes. These are viscoelastic, and they're actually designed to absorb that energy and to flex. And so we've normally seen, I'll say, approaching zero failures with our VGs because of the way that this viscoelastic tape works with all of the energy going on in the blade. As an example, these tapes have been used to hold traffic signs in place for years, used to hold glass on 50-story buildings for years. So they have some very unique properties, and that's why they work so well in this particular application. Okay. I mentioned earlier that we talk about highly confident of a 2 to 3% return or increase in AEP. And this just gives you an example of the number of profile turbines that we have already mapped and that we've already measured. So there's a dozen plus here, and you see that on the low end there's some that are the 1 to 1.5, and then there's some that are up in the 3.5 as well. But that band of 2 to 3 seems to be a sweet spot, and why we're so confident in what the vortex generators can return for you. Next slide, please. So we have EDF with its enhanced insulation. 3M is a material science company with the high reliability of the materials, be it for leading edge or the vortex generators. And then we use the competencies of SmartBlade to help us position them properly, makes for the VGs to be a very successful way to attack aerodynamic deficiencies and actually build in optimization. And so I think with that, I think that Jerome is going to talk to you about some comments from the owner's perspective. Jerome?
Yep. Thank you, Brett, and hello, everyone. So I will talk a little bit of why a blade maintenance program and AEP enhancements matter from the owner's perspective. And first, our mission as product owners or representative of the owner's interest is obviously to operate the project as safely, efficiently, and profitably as possible. So the first item which comes to mind is the worst case scenario, catastrophic blade failure. So a blade or debris from a blade falling to the ground is a major safety hazard to anyone nearby the wind turbine. So this is the type of event that we want to prevent from ever happening. In these scenarios, not only the blade is damaged, but often there's also damage to the tower and the nacelle. This is the type of event that could also create bad publicity for the company and the wind industry as a whole. Next, please. So now let's assume this is an event where the full blade needs to be replaced because it cannot be repaired in situ. There are numerous operational concerns from an owner's perspective. First, the repair costs, which include the direct costs such as the procurement of the blade, the mobilization of the cranes, the qualified O&M contractor, but also the indirect costs, which include the lost revenue and the lost tax benefits due to the wind turbine being offline. To give a little order of magnitude, this can amount to $500,000 for only one blade repair on the megawatt turbine. Secondly, the new blades are not very easy to procure. New blades might only be available on the other side of the country or even overseas, or they might not be available at all if the equipment is old and the mold production has been discontinued by the manufacturer. So if you're able to secure procurement of a new blade, then transportation of this blade, which can be up to 145 feet long and 40 tons, can be challenging, and it may take months to do that. It will require road permitting coordination with the transportation company, and it may require as well additional road reinforcements at the project site. So the landowner property and the crops may also be affected by the transportation of the blade through the fields. So if you're able to secure a blade and the same blade model is available, you can install it after you have weighted it against the existing blades to reach proper rotor balance. However, if the blade model is no longer available, you will have to buy a full new set of 3 blades, swap out all the existing blades from the affected turbine, and you have to keep the 2 old blades in inventory. So not only this is costly, but also this can become a long-term storage issue because of the size of these blades. After you have received a new blade, then you will have to deal with crane availability, weather conditions, availability of a qualified contractor, and these will dictate when you can actually perform the blade repair on site. So from an owner's perspective, those are like kind of the main operational concerns. Next slide, please. So when it comes to blade maintenance and blade enhancements, there are also additional contractual considerations. For example, often our power purchase agreements have minimum energy production guarantees in the contract. So to make sure you meet your contract requirements and avoid liquidated damages or even event of defaults, you want to ensure that your turbines are producing the highest AEP possible. If your equipment is still under warranty, you also want to ensure that your maintenance program is at least as stringent as the OEM specifications. This maintenance will document the condition of the blade, and we all will allow the project and the owner to maintain its warranty rights under the supply agreement. Permit compliance is another area where we owners are vigilant. For example, use permits typically allow for up to a certain noise level. So in some cases where you can see defects like damaged trailing edge, they can create a whistling sound and increase the decibel level at the site. So I'm not aware of any noise level which resulted in permit non-compliance issues. However, this noise can become an annoyance for the landowner and the neighbors. Additionally, most projects carry operational insurance to cover major component repairs, including blade repairs. One problem with the blade insurance coverage, though, compared to the other major component coverage, such as gearboxes, generators, or transformers, is that it is harder to distinguish between an unexpected failure and normal wear and tear. And it happens sometimes that some insurance providers might argue that the reason for the damage is normal wear and tear, and they might deny the reimbursement of the repair cost. So due to the high cost of these blade repairs, such large expenses can also become one contributing factor for the project and the project to actually fail some of its financial coverage ratios and the project's earnings to be trapped for months at a time. Next slide, please. So as a result, the benefits of a quality blade program are multiple. First, it keeps the project equipment maintained per the OEM engineering specifications and per the best industry practices. This will ultimately result in higher energy production for the project. Close monitoring of the defects will detect defects early on and will allow the project to perform less expensive up-tower repairs. So these preventive care will prevent damages from spreading to a point where the blades are not structurally sound anymore and need to be completely replaced. A maintenance program can also be tailored to local conditions. For example, the type of damage arising on an asset in Canada, subject to snow and ice, will be much different than those arising on an asset in Mojave Desert in California, where it would be subject to dust, sand, and high temperatures. So finally, and this is something difficult to quantify, but a better airflow, as showed on some of the slides previously by Brett, due to a good blade maintenance, will result in a reduced downstream wake effect for the other terms of the project. So they will also be able to generate more power. So from a financial perspective, a good blade maintenance program and blade enhancements will lead to higher revenues because the blades are performing more efficiently. Less blades replacements will lead to overall long-term operating expenses. And if blades are monitored carefully and repairs are planned ahead of time, then the owner can combine major component replacements to further reduce the cost. A good outcome from a good maintenance program is also that it will create more predictable cash flows, and it will make it much easier for the owner to manage its financial covenants under the project agreements. AEP enhancements, similar to the one described by Brett, have a positive payback in a matter of years and generate more energy for the project. So I think overall, from the owner's perspective, we can say that a quality blade maintenance program and AEP enhancements, they can be seen as an additional insurance policy, which reduces the operational cost and also allows the owner to extract more value from each turbine. And as we say in asset management, it actually makes the asset sweat. Now I will turn it to Charles for a quick recap.
Thank you, Jerome. It's always great to get an owner's insight. I'd like to recap with the 4 pillars of blade management. Inspection. Inspection is the foundation of a good blade management program. The inspection is the key to understand the condition of the blades for planned repairs in future years and budgeting accordingly. Repairs with a good inspection and with good inspections and photographs, you are able to budget accordingly for following years to manage the damage. Protection. As blades continue to get longer with higher tip speeds, we need to step up our efforts to provide protection to the high wear areas like leading edge. And upgrade. Take advantage of AEP upgrades like VGs early on in the life of the project to maximize ROI. I want to thank everyone for joining us today. We're going to go back to Cara for questions.
Thank you, Charles. Thank you, Jerome, and thank you, Brett. That's really good to see, and we've got an awful lot of questions to get through. So just a reminder to everyone that you can still send in your questions using the pop-up. If we don't get to answer your questions today, that's absolutely fine. We're going to be sending them all to EDF anyway, so they'll be able to respond to you directly on any of your questions. So please do keep sending them in. Don't think that just because we have a minute to go that we won't be able to get them asked. So to get straight into it, I'm just going to ask questions to the whole kind of speaker group, and you guys can just make sure to say your name as you're answering. So the first question is, have you done the GE 1.5 and what was the impact?
Yes, this is Charles. We have installed on the GE 1.5 platform. We see between a 1.5 and 3% increase depending on the type of 1X turbine you install the VGs on.
Okay, but what's the average last?
You say the average life?
Yeah, the average last. I mean, how long of service life?
Right, do you want to go ahead and take that one?
So I think if that's specifically towards vortex generators, we see them consistently 5+ years.
Okay. Can I put vortex generators on blades that have erosion?
This is Charles again. Yes, you can install VGs on turbines that have leading edge erosion. You will see an AEP increase, but you should always take care of your leading edge erosion first and then install VGs to maximize your AEP increase. Gotcha.
But let's assume that we don't have any erosion. I mean, how long is it going to take me to install VGs?
When we're looking at installing, this is Charles again, looking at installation of VGs, depending on weather conditions, you can usually install VGs within 1 day on all 3 blades.
Okay, but what about the LEP tape? How long about that?
This is Charles again. For LEP tape, it depends on the condition of the blade if you need to do any preparation. If you have to prep the blade, if you have severe erosion, it can take a day just to do the preparation. Depending on the installation method, if you're looking at platform compared to a boom truck, you're looking at 1 to 3 days. It just depends on the installation method you choose.
And
okay.
This is Brett. If I could just add a comment to that, Charles. One of the unique features of the leading edge protection tape, the 2.0, is that tape set can actually be applied in a wider window regarding temperature and or humidity, and so can allow installation teams to have to be more effective once on site compared to coatings and things like that typically.
Okay, so this is one question that came up during the webinar is, I mean, just why are there not sensors to detect blade damage?
This is Charles. I can address that one as well. The older generation of turbines did not have sensors that could detect aero imbalances. So usually when you have severe damage, you're going to have an aero imbalance on your rotor. The newer generations of turbines that have advanced load control, those are able to detect aero imbalances. Oftentimes those imbalances are due to sensors being off, but if you don't have a sensor problem, it can mean that you have a blade defect. So you should always take a look at your blades to see if you have any signs of damage when you have an aero imbalance fault. On the newer generation of turbines, probably in the last 5 years is where you're going to see that technology.
Okay. Well, a lot of the next questions we have are a little bit all over the place, so we might jump to one place and then back. So just bear with. So I guess kind of this question's asking. I mean, you know, when you're looking at the maybe this is one to Jerome as an owner. I guess we're wondering is how do you actually perform the evaluation of any AEP gains or losses when you've applied new technology? How are you measuring that?
Yeah, so you first look at obviously the cost of the installation and the downtime of the turbine for doing the installation, and how much loss revenue that would be incurred by such installation, and then you compare to how much gain you make from that AEP enhancement. So I think like it's important to have like a benchmark to see what other turbines and what other blades have been able to recover on with some AEP enhancements to be able to do that payback analysis. But that, yeah, once you have like the analysis of how much energy you can recover, comparing this to the cost of installation, then you can figure out your payback in a number of years and see if this is an investment you want to make.
Gotcha. So a different question. I mean, why is the maintenance in the first 10 years so key? And then the second part of this question, I mean, is what should this other owner be looking to experience after 10 years? So what are the nightmares in that first 10 years that they need to be looking out for?
This is Charles. I can address a couple of those. In the first 10 years is usually for most sites that have been constructed lately, they have PTC credits. So you want to maximize the performance of your assets to not only capture the megawatts, but also to capture the PTC credits. Within the first 2 years, most turbines come with a manufacturer's warranty. With all components, you have infant mortality, you have components that fail. You want to leverage your end of warranty inspection at that 2-year mark to try to drive as much cost back on the OEM. And after the 10-year mark, you still have costs. You still have to have a good blade maintenance program, but you don't have the same revenue flow as you did during the first 10 years.
Okay. There's a question here about the tapes and the actual life of the tapes.
Okay, so this is Brett. I guess the best way to serve it up is if we use, 3M has been involved in leading edge protection on blades since the Vietnam War, and worrying about rain erosion on helicopter blades. And technologies have advanced, and as we've developed solutions for leading edge protection, durability and long life are a couple of the key things that we look for, and that we've designed and developed around. Wind Protection Tape 1.0, again, when you expose it to a rain erosion testing, which is kind of an industry standard, we see that it was lasting, like I say, about 9 hours in that test, which is about 5 years in the field. What we've done since then is we've actually optimized the polymers, and we've actually done some work with the adhesives to strengthen the bond and also to allow it to absorb the energy from moisture and things like that from the rain. So that's where in that test environment, it went from 9 hours to 50 hours before failure. So there, it's only been out on the market now for about 1.5 years. So you have to assume if there's a correlation that 9 hours equals 5 years, and now we're at 50 hours for the exact same test, that's where we look at that life of a blade, 15, 20 years is when properly installed, I think is what we're trying to position or demonstrate. Again, every site is so unique. So if you're on the coast in super high rain environment, or you're in the desert, it depends is kind of the asterisk, but it's roughly 4 to 5 times the performance is what we expect.
Mm-hmm. Okay, so I guess a lot of
this is Charles. I'd like to add one more thing. One of the reasons EDF has went with the tape is we have in the past used the coatings, and the coatings do have a very narrow weather tolerance. Also, when you're applying the coating, you have the humidity and contamination risks. That coating is meant to be installed within very controlled environments. With the tape, we can install it within that wide range of temperature ranges and humidity ranges, and it's a very quick installation. Our techs can install it once the surface is prepped within 45 minutes.
Okay, perfect. So we've got time for an extra just very couple of questions. I know we've already passed the hour. But this question is, I guess, related to the development of blade design. So obviously a lot of blades now are maybe more modern. We would hope that they would have better, they would withstand kind of leading edge erosion better. Is that the case? And where do you think the development of kind of blade technology can go in the next couple of years?
So this is Charles. The one thing I can say with respect to the design of the blades is, from an owner's perspective, if possible, you should always look at installing LEP at the factory. That's going to be the most cost-effective way to do it. Sadly, not many owners do this, so this is usually an add-on later on in the life project.
Okay. And how much of the leading edge should be protected with tape? Is it a length? Is it a certain amount of length, or is it a percent, or is it just the whole thing?
So this is Brett, and typically what we see is the outer third, outer half to the outer third is where the higher tip speeds are at, and where the most protection is needed.
Perfect.
So one thing I'll add is that as the turbines get longer, as our tip speeds increase, we are going to have to install LEP on more of the blades. So it's going to probably move closer to half of the blade as these wind turbine blades get longer. We do see that we have parks with different size rotors on them, and we are seeing different levels of erosion on the larger rotors and the smaller rotors.
Okay, and then a final question before we kind of summarize, and this is a very good question. I think, and especially if you've worked in Canada, is what's the impact of the VGs on noise emission?
So this is Brett. There are specific attachments or devices like serrations and things like that that are specifically intended to quiet noise. The primary objective of a vortex generator is to increase the AEP and to basically eliminate or reduce that stall. So one of the benefits of that is that it definitely does not add noise, and more than likely seems to quiet because the air is not that big, bold, turbulent signature, but it's been reduced.
Okay, perfect. So just before I wrap up, I mean, would each of the panelists, maybe starting with Charles, then Brett, then Jerome, would you each be able just to kind of give a quick sentence or two about what you hope the audience have taken away from this webinar today? If they could take away one piece of information, what would you hope that would be? So maybe Charles first.
Thank you. Yes, the one thing I would like to take is for owners to look at their blades early on in life. The earlier on you look at the blades, the sooner you can start to build your blade maintenance program.
Perfect. And Brett?
I think the key takeaway is that there is AEP to be gained, I'll say, at the margins. Like we kind of highlighted, it's 2 or 3% here with the leading edge, it's 2 or 3% by looking at vortex generators. So there are some lower cost solutions that can increase their AEP and put more money coming through their machines.
Okay. And Jerome? Okay, well, I'm just going to wrap up then. So, I mean, thank you all for getting involved. I mean, I'd really like to thank, obviously, 3M and EDF for helping us put this together and for introducing such good content. And also thanks in advance for answering all of the questions I'm about to send them that didn't get answered today. So this webinar has been a real huge success. And I hope you, as an audience, have certainly gained an awful lot more from this than you'd even hoped, which is really good. Before you all send me emails afterwards, just want to reiterate that the recordings will be sent to you around this time tomorrow automatically by GoToWebinar, and then we'll be promoting them ourselves over the next few weeks. So the only thing left to ask there is, where do we go from here? I mean, it's clear that the long-term value of wind investments could be crippled through a lack of understanding on key operational issues such as blade maintenance by many owners. Furthermore, this lack of clear understanding by large and small owners alike is really hurting our ability to optimize production and, crucially, drive up profitability of wind globally. This is why more than 600 of the industry's most forward-thinking utilities, IPPs, developers, OEMs, and innovators are all gathering at the 10th Annual Wind Operations Dallas 2018 this April to gain the insights they need to boost profits through successful O&M and asset management, by reducing LCOE, by increasing AEP, and by driving up their revenue growth. This year's program includes a first ever dedicated stream for blade technicians, managers, and innovators that includes can't miss new case histories from the likes of Vestas, E.ON, Leeward, Duke, and Eloan, formerly Gaston, and so many more before special topic networking and blades roundtables. I mean, this is not to be missed. If you've enjoyed this webinar, then this is the next step for you. Not only this in blades, but this year also brings together 8 incredible conference streams into one, with all new powerhouse opening keynotes set to shine a spotlight on critical new trends in repowering strategies, new visions for service contract incentives, an essential guide to lean operations, and even a critical guide to the role of blockchain in renewable energy. There really is a lot to take in. What's more, we'll follow this up with a succession of invaluable streams covering everything from self-service business models to digitalization challenges to new case studies from the likes of DTE, EDPR, and so many more on gearbox issues, electrical maintenance issues, BOP, asset risk management, and so much more. I'm not entirely sure that anyone can afford to miss out, so make sure you visit the Wind Operations Dallas 2018 website to find out more right now and secure your place at the #1 meeting point for business leaders and wind decision makers globally. I hope you and your team can make it, but do just get in touch with me at the details that are on the screen if you have any questions at all. And without any further ado, I'd like to thank again all of the team at EDF and at 3M for making this webinar possible. Goodbye, everyone. Thank you.